Have you ever wondered what it would feel like to step outside the river of time, to leap forward into the distant future, or walk backward into a forgotten past? It is a question that has haunted philosophers, mystics, scientists, and storytellers for centuries. Time travel. Is it possible? Or is it nothing more than a dream? A story we tell ourselves because we are trapped in the one-way flow of time. Humanity has always been obsessed with escaping the present. We imagine machines that spin like clocks, wormholes that bend the universe, portals glowing in the night. But behind the science fiction lies a deeper mystery. Time itself. What is it? And can it truly be conquered? This is the story of time travel, where physics collides with imagination, where equations bend reality, where the past, present, and future are not as separate as they seem. Before we can even dream of traveling through time, we must first understand what time actually is. Most of us treat it as a ticking clock. Seconds, minutes, hours. A steady rhythm, forever marching forward. But physics tells a stranger story. In the universe of Albert Einstein, time is not absolute. It bends and stretches, woven together with space itself. This fabric is called space-time, and it doesn't tick the same way for everyone. If you move fast enough, time slows down for you. This is not theory, it's proven. Astronauts orbiting Earth age just a little slower than the rest of us. Moons, tiny particles traveling near the speed of light, live longer than they should. Time is flexible. This revelation opens a doorway. If time can stretch and bend, could it fold? Could it allow us to step from one century into another? Traveling into the future is not only possible, it's inevitable. We are doing it right now, 1 second per second. But physics allows us to go faster. Einstein's theory of relativity reveals a strange truth. The faster you travel, the slower time moves for you compared to those you leave behind. This effect is called time dilation. Imagine boarding a spaceship, accelerating close to the speed of light. For you, only a few years might pass. But back on Earth, centuries could unfold. This is not fantasy. It is mathematics. It is reality. The universe has already given us the tools to travel forward. What holds us back is not the laws of nature, but our engineering. We lack the energy, the technology, the means to push a human body safely to such extremes. But one day, if humanity dares, our descendants could look into the night sky and know that by riding near light-speed ships, they can leap across millennia. The future, at least, is waiting for us. But what about the past? This is where time travel becomes truly controversial. Forward travel is permitted by the universe. Backward travel, however, threatens to break it. Imagine going back and preventing your grandparents from meeting. The paradox unfolds. If they never meet, you are never born. And if you are never born, how could you have gone back in time in the first place? Physicists call this the grandfather paradox, and it is the reason many scientists believe backward time travel may remain forever beyond reach. But there are loopholes. The universe may not forbid visiting the past. It may only forbid changing it. Some theories suggest the past is locked, unchangeable. You can visit, but not interfere. Others suggest that changing the past creates a new branch of reality, a parallel universe, splitting from our own. Time becomes not a single arrow, but a tree, each decision birthing a new path. If this is true, then traveling to the past may not rewrite history, but create another one. If backward travel is possible, how could it work? Enter one of the most fascinating ideas in modern physics: wormholes. Imagine space-time as a sheet of paper. If you fold it, two distant points can touch. A wormhole is a tunnel through that folded fabric, a shortcut across space and time. In theory, if you could create and stabilize a wormhole, you could step through one end and emerge not only in another place, but in another time. But there is a catch. Wormholes are unstable. Left alone, they collapse faster than light. To keep one open, you would need exotic matter, stuff with negative energy density, something we have never observed in the quantities required. Still, wormholes remain one of physics' most tantalizing bridges between science fiction and reality. They suggest that time travel may not be forbidden. It may only be extremely, almost impossibly difficult. Even if wormholes exist, there is a deeper mystery. Why does time seem to flow in only one direction? In physics, most fundamental laws are time-symmetric. Run the equations backward, and they still work. Yet in our everyday lives, eggs break but never unbreak, smoke rises but never falls back into the match, and we grow older but never younger. This is the arrow of time, and it is powered by entropy, the natural tendency of order to decay into disorder. The universe itself is moving from a state of low entropy at the Big Bang toward higher entropy today. If we ever travel backward, we must confront this arrow. Are we truly moving against the fundamental grain of the cosmos, or is our perception of time just an illusion born of entropy's grip? Beyond relativity lies the even stranger world of quantum mechanics. Here, particles do not behave like tiny billiard balls. They blur, they overlap, they exist in many states at once. Some physicists believe quantum mechanics may hold the key to time travel. In quantum theory, events are not strictly determined until they are observed. This has given rise to interpretations where every possibility splits into a new universe. If so, then paradoxes may dissolve. Going back and preventing your birth would not erase your timeline. It would simply create another. Others speculate that particles themselves may already travel backward through time on the quantum scale. If this is true, the universe may already allow time loops, tiny, hidden, woven into reality itself. Quantum physics doesn't just question whether time travel is possible, it questions what time even is. The paradoxes of time travel are some of the most mind-bending puzzles ever imagined. The bootstrap paradox asks, what if an object or piece of information is sent back in time and becomes the very cause of its self-existing? For example, imagine giving Shakespeare his own works. He publishes them. Centuries later, you take them back again. Who truly wrote them? Then there is the predestination paradox. What if you travel back in time to prevent something, but your very actions cause it to happen? Are we trapped in fate, unable to break the chain? These paradoxes are not just thought experiments, they are clues. They suggest that if time travel exists, it must follow rules stranger than anything we can yet imagine. Suppose just for a moment that humanity cracks the code. Suppose we build a machine that bends time. What would it mean? The consequences would be staggering. Imagine historians walking among dinosaurs, scientists watching the birth of stars, families reuniting with those they lost. But with wonder comes danger. The misuse of time travel could unravel civilizations. It could be weaponized, exploited, twisted. Entire timelines could collapse. Power over time is power over reality itself. Perhaps this is why, if time travelers exist, they remain hidden. Perhaps the laws of physics or the laws of wisdom prevent us from holding such a key. In the end, time travel may not be about machines or wormholes at all. It may be about us. We already time travel every day, in memory. The past lives inside us, painted in flashes of joy, grief, love, and loss. The future lives in our hopes, our fears, our dreams. Some physicists suggest consciousness itself may be tied to time in ways we do not yet understand. Are we moving through a block universe where past, present, and future coexist, and our minds simply light up one moment at a time? Or is time itself created by consciousness, an illusion woven by the act of perception? Perhaps time travel is not about breaking free of time, but about understanding what time truly is. From H.G. Wells's Time Machine to Hollywood blockbusters, time travel has been one of humanity's greatest stories. We use it to imagine second chances, alternate destinies, impossible adventures. But fiction is more than entertainment. It inspires science. Many physicists today admit they were first drawn to their field by stories of time travel. What was once dismissed as fantasy is now written in equations, tested in experiments, and debated at the edges of knowledge. Fiction dreams, and physics asks, why not? So where does this leave us? Time travel remains perched on the razor's edge between science and fiction. Physics permits glimpses into the future, but the past still hides behind paradox. Wormholes beckon, but collapse. Quantum mechanics teases, but refuses to answer. Perhaps time travel will one day be mastered, or perhaps the laws of the universe protect us from it. Either way, the journey toward understanding time is one of humanity's greatest adventures. Because in the end, time travel is not just about machines or equations. It is about our longing to escape limits, our hunger to see what lies beyond, our refusal to accept that the present moment is all we will ever know. The question remains, is time travel physics or just fiction? The answer may shape not only our future, but the very meaning of time itself.